Well, we are over the halfway point of our curriculum. We have just finished the first equilibrium chapter of this Big Idea 6. Now we are on the second portion of it, which exclusively deals with acids and bases. It's obviously more in depth than you've seen before, but if you understood the ICE problem solving methods and how to write a K expression from the last unit, you should be good. This first lesson is just really a review of acid-base concepts, most of which you should be familiar with. So at this point, you should be able to identify a substance as being an acid or a base, usually based on the Arrhenius or the Bronsted-Lowry theory. You should be able to name acids and bases to some extent and also describe the pH scale in terms of what is acidic and what is basic. At the end of this lesson, you should be able to classify substances as being acidic or basic based on both the Arrhenius and Bronsted-Lowry theory, identify conjugate acid and base pairs, identify strong acids and bases. This is something that you do need to memorize as a list, and also understand the types of reactions that acids and bases can undergo. So first off, according to the Arrhenius theory, an acid is a substance when dissolved in water increases the concentration of hydrogen ions. So you could see this as hydrogen ions, or you could see it as hydronium ions. But either way, it's a substance that dissolves in water to yield those ions as a positive ion in solution, and they have pHs less than 7. An Arrhenius base will dissolve in water as well, and it will increase the concentration of hydroxide ions in the solution, and their pHs are greater than 7. So what you would see for an Arrhenius acid is you would have this formula. So just the generic formula, the H for the hydrogen, the A would be the the anion for the acid. When it dissolves in water, that's where you get these hydrogen ions in solution, and whatever the anion is that also made up the acid. Bases produce hydroxide, so you have a cation with this hydroxide anion that when it dissolves and dissociates, you free up hydroxide ions in the solution. The problem with the Arrhenius theory is it only works for bases that have hydroxide ions in them, and not all bases do. Another problem with it is it only works when you're talking about aqueous solutions, and some reactions can take place in a gas phase, even though they're acidic and basic. So then we have this Bronsted-Lowry theory, and in Regents chemistry, we were taught this acronym BAD, whereas bases accept hydrogens or protons, acids donate hydrogens or protons. So an acid is a proton donor, a base is a proton acceptor. So there's your AD and here's your BA. Now proton and hydrogen ions are synonymous because if I take a hydrogen atom with its one electron and it loses that one electron, all I'm left with is one proton in the nucleus. So it's the same thing. Some substances can be what is called amphiprotic or amphoteric. That means that they can either accept hydrogens or donate hydrogens. So if this ion is accepting a hydrogen, it would become H2CO3. If it were to donate a hydrogen and act as an acid, then it would become carbonate ion. Same thing here, accepting a hydrogen, this would be the product. Donating a hydrogen, I'd be left with the sulfate ion. Accepting a hydrogen, I have the hydronium, donating a hydrogen, and I'm left with a hydroxide. The key here is for something to be amphiprotic, it has to have at least one hydrogen because it's got to be able to donate it in order to act as an acid. This is an example of a reaction using this Bronsted-Lowry model where I can have a substance reacting with water, and if that substance where am I going here? Oh, if it donates a hydrogen to the other reactant, so this is acting as a donor, acids donate. So the HA acts as an acid because it donates a hydrogen to the water. When it donates its hydrogen, it becomes this anion, and whatever is left over after it donates is the conjugate base. So basically you have these partnerships where on the reactant side, you have a formula with something that has the hydrogen present, and on the product side, you have the only difference is you've lost a hydrogen. Same thing here. This other partnership, I have a formula that's lacking a hydrogen that the product has now gained. So you need to be able to identify these conjugate acid-base pairs. So a Bronsted-Lowry acid can lose protons where am I? Lose protons to become a conjugate base, which is everything that remains of the acid after it lost its proton. And a base can accept protons to become the conjugate acid of the original compound. And again, it's formed when the proton is donated. So reactions between acids and bases will always yield the conjugate pair. So really what you need to be able to do in the context of a chemical reaction is to identify substances being an acid or a base, and then what the conjugate acid or base is. And we're going to look at examples of that. So here in this first reaction, which I think is the same thing from the last slide, you need to be able to pick partners. So when I teach this in Regents Chem, I say pick something on the left and something on the right where the only difference between them is a hydrogen. So I would have HNO2 and NO2 minus, and then H2O and H3O. Once you've established those partnerships, that is a conjugate acid-base pair. One of those things is an acid and one of those is a base. Now, the way that you identify what the acid is, that in that partnership, the acid is the one that has the extra hydrogen, the conjugate base is the one that doesn't. And then the same thing for the other partnership. The acid is the one that has the extra hydrogen, the base is the one that doesn't. Another thing to keep in mind is you can't have the same thing on the same side. So once you identify one of your pairs, you're good for the whole reaction. For the next equation, your conjugate pairs would be the NH3 and the NH4, because the only difference is the extra hydrogen. And your other partnership would be your H2O and your OH, again, because the only difference is a hydrogen. So in the first pair of NH3 and NH4, the NH3 would be a base because it's lacking a hydrogen that the NH4 has, and then my other partners has to be the opposite arrangement, and it makes sense because the H2O has one extra hydrogen than the OH. So a conjugate pair would be the set of partners, one on each side of a reaction. So we have an acid and its conjugate base, we have a base and its conjugate acid, etc. So if you have this sort of situation, you could be asked this in a multiple choice question, to find the conjugate acid. Well, what that's saying is that all of these things are bases, which means they are lacking a hydrogen. So what does this become when it gets a hydrogen? NH4 plus. What does this become? H2S. And remember, it's accepting a positive, accept a proton. So it's a positive ion it's accepting, which makes sense that when this negative ion accepts a positive hydrogen, it neutralizes it into H2S. The HSO4 accepts a positive hydrogen, becomes H2SO4, and the H2PO4 minus accepts a hydrogen and becomes H3PO4. So bases can gain hydrogen ions to become the conjugate acid. And then the opposite, find the conjugate base. So all of these are acids. They're going to donate a positive. So they're going to become less positive than they were before. So this is going to be ClO4 minus. This will be Cl minus. This will be HSO4 minus. And this will be H2PO4 minus. Ta-da! So you should be able to, at this point, identify a substance as being an acid or a base according to either the Arrhenius model, looking for hydrogens or hydroxides, or the Bronsted-Lowry model, where you identify conjugate acid-base pairs in the context of a reaction. The next part here is just looking at the strengths of acids and bases. We will spend time in the next lesson looking at how to calculate pH values and what that means. But when you see something called a strong acid, you are saying that it completely dissociates in water, that nothing remains intact as a molecule. Strong acids have weak conjugate bases. That is something that you need to know. If you have an acid that is considered to be weak, that means that it only partially dissociates in water. So that means that depending on the strength of the acid, and there's numerical values associated with this, either a high percentage or medium percentage or a low percentage of the molecules will actually dissociate in the water. So you would still have some molecules intact there. They would also have weak conjugate bases. So this chart just shows you some strong acids, and you actually have to memorize a list of these. Here we are. So strong versus weak acid. So a strong acid, the ionization lies far to the right. So that means that it's heavily product favored. And for strong acids, they dissociate so much that we don't even put them into an equilibrium. We just say that it's a one directional arrow. The concentration of the intact acid is so small that you would always just assume that it's zero when you're doing any sort of calculation with the strong acid. The only concentrations you're really concerned with are the concentrations of the anion that's left and the hydronium. So another way that this could kind of be written is that HA, you don't need that, plus A minus. You have a full dissociation. It separates completely. You need to know this list of strong acids. Write it on your bathroom mirror, tape it to your bedroom ceiling. Don't tattoo it on your body, but you need to know these. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, phosphoric acid, sulfuric acid, and perchloric acid. These are the must know for strong acids. Any other acid that you're given is not strong. So when you're doing calculations involving any of these 7, they will be done differently than calculations involving any that are not these 7. Okay, so for any of these 7 acids, you are assuming full dissociation. So what that means is the concentration of the acid is going to be equal to the concentration of the hydronium or hydrogen ions it dissociates into. So for example, if I have a 3 molar hydrochloric acid, hydrochloric is a strong acid. It fully dissociates into hydrogen ions and the chloride ions, or you could write this as it can react with water to form hydronium ions and the chloride ions. The concentration of the acid is the concentration of these ions, because for every 3 moles of the HCl, I could get 3 moles of hydrogen and 3 moles of chloride ions. That's what this statement means here. So this image on the left shows just what I was saying with the concentrations, that if I have a strong acid, the concentration of the acid is equal to the concentration of all the ions when they dissociate. But if I have something that's a weak acid, when I put it into water, it actually establishes an equilibrium further to the left. It's more reactant favored, so I will still have intact, a decent quantity, you can see here. I still have a decent quantity of intact acid molecules and a very small quantity of dissociated ions, whereas with the strong acid, it all completely dissociated. So this truly will just be an equilibrium reaction. So when you do calculations involving strong acids, they're simpler because you have the concentration right off the bat. When you have weak acids and they establish an equilibrium, it will require an equilibrium constant, an acid equilibrium constant, or if it's a base equilibrium constant. That will kind of give you an indication of how much dissociation there's going to be, or how little in this case. The final portion of this lesson is just to review reactions that acids and bases in this case, and then just acids in the other, can undergo. The first is neutralization, and we talked about this very early in the year when you were just baby AP chemistry students, right? You're professionals now. So neutralization reaction, this is like Regents stuff. An acid plus a base will result in the formation of a salt and water. When you have a strong acid reacting with a strong base, you will end up with a salt that is neutral, and the water and the pH will equal 7. If you do not have a strong acid and strong base combination, if you have a weak acid and a strong base, or a strong acid and a weak base, or a weak acid and a weak base, it's a little bit different. We'll get into that in this unit. It's super fun. Not really. But when you're dealing with strong acids and strong bases, your pH will equal 7. So this would be an example of a strong acid. How do you know? Because you've memorized your list of strong acids. And this is a strong base, which we'll talk about the strong bases you need to know. There's only a few in the next lesson. But we have full dissociation of both of these. So you'll end up with water, which actually this isn't balanced, silly me. You'll end up with water, your neutral substance, and then a solvent. The other type of reaction you need to know is just for acids, that acids will react with most metals. I don't know if you remember, you had a reference table in Regents Chem activity series. It was a table J, and it was like a whole list of metals from more reactive to less reactive, and then a list of non-metals from more reactive to less reactive, and hydrogen was on there. And we said that any metal that was above hydrogen would react with an acid to form hydrogen gas. So these three, copper, silver, and gold, were the three that were below hydrogen, so you would not get a reaction if you dropped any of those three into an acid. But if you dropped any other of those more active metals into an acid, then you would get a reaction occurring. So if I took a piece of magnesium, dropped it into a solution of hydrochloric acid, it's a single replacement reaction. The magnesium is more reactive than the hydrogen, so it kicks the hydrogen out, and it's released as hydrogen gas, and you're left with magnesium chloride solution. Same thing happens if I would take zinc and drop it into hydrochloric acid. The hydrogen would get kicked out. The zinc would take its place. I'd be left with zinc chloride. You probably did labs with this in Regents Chem. That's where you did like the hydrogen explosion test, where your reaction was happening and you trapped the gas with like a stopper or another test tube on top. And then you took, this is a beautiful art lesson, this is like Pictionary. And then you took a burning wood splint and you separated the two test tubes and you put the wood splint and you got that loud like whistling pop. That was one of these reactions. So yeah, I should teach art. So we're done now with this little section of can you write acid-base reactions. It's more recognition than anything else. And so completing this lesson, you should know how to classify acids and bases based on two different theories, identify conjugate acid-base pairs in the context of a Bronsted-Lowry reaction, identify strong acids and bases. Again, I'll go over the strong bases in the next lesson. It's very brief. And you should also be able to explain and write acid-base reactions. So that's your first little tiptoe into the baby pool of acid-base equilibrium stuff. Look, it's not so scary, but just you wait. Mwahaha. It's late.